And I think we can get started. I'm super excited about this presentation. Today we have an amazing speaker. Bachir El Khadir is going to tell us about polynomial optimization, semi-definite programming for robot motion planning. So Bachir is a Goldstein Fellow at IBM Research in New York. He received his master's from École Polytechnique and he got his PhD in operations research and financial engineering from Princeton University. And he's broadly interested in polynomial optimization for dynamical system control and machine learning. But today, again, he's going to tell us a little bit more about very cool application to motion planning for robotics. So Bachir, thanks for being virtually here, and welcome, and take it away.
Thank you so much for the very nice presentation. I'm super excited to be here and to be able to present this work to you. So this is joint work with Jean-Bernard Lasserre and Vika Sindwani. And yeah, today's topic is really about motion planning. But the goal of today is to present to you some of the tools that people are not that much aware of. And we're going to talk about a very nice connection between semi-definite programming and semi-definite programming and moment optimization. And we're going to see how the synergy between these two fields would lead to very nice solution techniques to the problem of motion planning. And actually the synergy and these tools are going to be broadly applicable to a wide range of applications beyond also motion planning. So there's a lot of work to be done, and it's really exciting. So with that being said, let me just jump right into it and present the problem to you. So motion planning, what it is, what is it? So you have a starting point. And then you have a goal you want to reach. Maybe there are some obstacles along the way, and these obstacles could be varying with time. And what you want is to find a path, and actually the shortest path that goes from the start to the end, while not colliding any of the obstacles along the way. Okay, so that's the problem. And here I'm interested purely in the geometrical problem. So there's no dynamics involved. The robot is simply a point in space and it can move however you want, as long as the path is continuous. And sorry, let's talk a little bit about these obstacles. So for me, each obstacle is defined by a polynomial inequality. So you can see here, each obstacle is given by an inequality g of t and x, then negative. So g here is a polynomial function in t and x. So t is time and x in space. So the dependence on time is what is going to allow me to have obstacles that are moving, morphing, varying with time, etc. So more formally, what we're interested in is finding a path, and a path is really a continuous or a differentiable function that goes from the interval of time 0 capital T to Rn. And I want the shortest path. So the length of a path is given simply by the integral between 0 and capital T of the L2 norm of x dot. So x dot is the time derivative of x. I want it to start from x0. I want it to end at x capital T. And I wanted to avoid obstacles. So let's parse this last constraint. So this constraint is indexed by k. So k indexes the obstacles. K goes from 1 to m. M is how many obstacles I have. And t is time. So this is saying that for any time t, if I plug in t and x of t, where I am inside this function gk that represents obstacle k, I want this to be negative, meaning I want to avoid obstacle k at time t. And yeah, so I haven't done anything. I have just taken the problem and just written it as an optimization problem. And now the question is, how can we attack this problem and how can we go from here? So hopefully the setup is clear to everyone. And I forgot to say this at the beginning, but if there are any questions, feel free to stop me. I think you can raise your hand on Zoom or something like that, or I will try to keep an eye on the chat as well. If something is really unclear, please stop me and I can answer that and I can clarify. Also, you will have a chance at the end of the talk if there are more questions. So back to this. So this is the problem that we're going to be looking at today. So before we move any further, so I mentioned briefly that this function g that represents the obstacles is a polynomial function. What do I mean by a polynomial? A multivariate polynomial in a polynomial function that depends on a variable that is a vector of variables y1 to yn. So polynomials are interesting. So these are functions where the only operations we're allowed to do is multiply variables together. So this includes raising variables to some given power. Okay. So when you do this, when you multiply variables together, the term that you get is called a monomial. So here, the yi's are the variables, the alpha i's are integer values that we call the powers. And we, just as a notation, notational shortcut, if you want, we're gonna call this monomial y to the power alpha. So y is a vector, alpha is a vector, and what I mean by this notation, vector to the power another vector is simply, you take the powers of the entries and then you multiply them together. And also, we call the degree of the monomial so the sum of these powers, we call them the degree of this monomial, and the degree of a polynomial is simply the highest degrees of all these monomials. So anyway, so monomials are the building blocks of these bigger functions that we call polynomials. Now, okay, so now that I defined polynomials to you, what kind of sets can we describe by polynomial inequality, right? So the simplest way to think about this, or the simplest possible polynomial functions are linear functions. So linear functions, you can think of them as polynomial functions of degree 1. So when you have a linear inequality, what you really have is a half space, right? So a linear equality is a hyperplane, and the linear inequality is a half space, right? But you can also have higher degree polynomials. So if you have quadratics, you can have things like the ball, and with more complicated polynomials, you can get more complicated shapes. And I should point here that polynomials are nice because they have this algebraic structure, and it might seem arbitrary to restrict ourselves to polynomial functions. And the answer to that is, as we will see, working with polynomial functions will enable us to use a lot of powerful tools from semi-definite programming and moment optimization, and I will get back to that in a second. But also polynomial functions, surprisingly, if you've never encountered them, are in a sense universal approximators. Any continuous function or any reasonably looking function can be uniformly approximated with polynomials over compact sets. So basically you can always, if you allow yourself a degree that is high enough, you can approximate any function that you want. Anyway, so these are the sets that you can have described by polynomial inequalities. And you're not limited to a single inequality. You can have multiple inequalities. So for the sake of this talk, I will stick to one inequality, but just for simplicity. But the ideas I'm going to present to you can be generalized to multiple inequalities if you want. And multiple inequalities give you more flexibility. For example, if you have multiple linear inequalities, then you're looking at intersection of half spaces. So intersection of half spaces, actually it has a name. So these are the sets that we call polyhedra. So these are feasible sets to linear programs if you've taken an optimization class before. Okay, so I presented to you, polynomials, what we can do with them. Now let's go back to the motion planning problem, right? So if I describe a motion planning problem to you, how do you compute the shortest feasible path? So by feasible, I just mean a path that does not collide with all. And here,
let me stop for a second. I think you're waking up every now and then. I think it's still understandable so far, but I don't know if you want to try unsharing screen, and when you click share, you also say optimize video. That might be a little bit smoother.
Yeah.
Again, it's understandable. We were able to follow so far, but
yes. Yes. Okay, it's asking for my password. I hope you cannot see this window. Or
we cannot.
I think I can do, if the audio breaks, I can switch to my phone for audio. If you cannot hear me well, and I can use my internet connection, my Wi-Fi for videos. But anyway, if it really
so now
gets
your video
bad,
is good, but the slide seems a little bit cut off. And can you just go back to the previous slide and go back to this one?
Oh, it's probably because of this. Wait. Okay, is it better like this?
Better, but we still see it cut. The lower part of the slide is cut.
Oh, the lower part of the slide is cut. Okay, let me stop sharing and share again.
Okay.
Let's hope. Can you see the full slide now?
No, I still cut. And I believe it's cut also for the others. So my side, I still see it. The lower half is just gray.
Okay, so maybe it's because I did this optimized. Is it still cut?
This is good now. Yeah.
Okay,
in the
so
worst case, if you keep breaking up, maybe I will. Yeah,
we'll
I think should work out. Okay, thanks.
Okay. Yeah. So for the listeners or the people watching that don't know, so I am in Morocco right now, and my Wi-Fi connection is not. I'm just in a hotel room, so my internet connection is not the best. So I apologize for that, but hopefully you can still get the gist out of this talk. So going back to the problem of interest, the motion planning problem. How do we actually compute the shortest or the length of the shortest feasible path? And I would say there are three main families of algorithms for doing exactly that. There are the first family, which give you upper bounds on the length of the shortest feasible path. And the way they do that typically is by providing a feasible path. So whenever you can compute a feasible path to a motion planning problem, you can compute the length of this path, and that gives you an upper bound. And algorithms of this kind could be, for example, something like RT. So these are algorithms that sample points at a little bit at random in the space, and then connect nodes in case there is no. So there is an edge between two nodes if there is no obstacle along that segment. And then once you have this discrete graph, you can compute the shortest path inside this graph by some classical algorithm like Dijkstra or something like that. But you can also do some kind of local search using a gradient-like algorithm. So I said that the motion planning problem is an optimization problem. So you can apply any one of the many algorithms that can attack optimization problems and find local solutions. So that's one. That's the first family of algorithms. The second family is what I call exact methods. And so exact methods, I mean something that takes the problem and gives you the exact solution, gives you really the length of the shortest feasible path. And to my knowledge, there is only one type of algorithms which are all based on computational algebraic geometry. So if you're a little bit familiar with this topic, you can formulate the motion planning problem as a feasibility problem of a bunch of polynomial inequalities, and you can do quantifier elimination, etc., and you can solve the problem exactly. Now, the problem with that, and there is a big problem with these methods, is that they are super expensive. So think, something that depends exponentially on the dimension or doubly exponentially in the dimension. So quickly, in practice, you would not be able to use any one of these methods, at least as they are, without any modifications. It's out of the question for any reasonably sized problem. The third family of algorithms give you lower bounds. So that's an interesting one, right? So if you use, for example, RT and find some path for your problem, it's not going to be optimal. If you're not that lucky, it's not going to be optimal. It would be a good thing to kind of have a bound on how far you are from optimality. And you can get this by computing a lower bound on the length of the shortest feasible path. And again, to my knowledge, there is no algorithm that really gives you lower bounds. I mean, how would you even go about this? How can you find the lower bounds over all feasible paths? That seems like a hard thing to ask. But as we're going to see, we're going to find a way to do exactly that. So today, what are we going to do? So today we'll show you how to attack the motion planning problem based, as I said, on techniques that come as a result of combining moment optimization and semi-definite programming. And we will tell you in a slide what I mean by that. And these methods will give us upper bounds, meaning it will provide some feasible paths for the motion planning problem, but also, and this is the most important thing, they will give us lower bounds. And that's really interesting. How can you find lower bound to a problem like this one? And then we're going to see something. So I said, these methods are based on semi-definite programming. And if you if you have some experience with them, you know that there are some scalability issues when the size of the problem gets bigger and bigger. So for this method that I'm going to show you, there is one parameter that we're going to call R. This is an integer. And as the user, you get complete control over it. So if you pick this R to be very small, what's going to happen is you're going to get an algorithm that runs super fast, but might not give you the best solution. And if R is too large, it will take forever to solve, but it will give you a more precise solution. So there is a parameter, there is a knob you can play with that that can trade off efficiency for accuracy. And we will see in a second what I mean by that. Okay, so let's do a right. So just looking at the chat, I can possibly also disable my video if it helps. If at some point it really gets bad. So before I move any further, I'm gonna spend 2 or 3 slides just telling you what I keep saying again and again: moment optimization, semi-definite programming. What do I really mean by that? So for this detour, forget the motion planning problem again, and let me just tell you what moment optimization is. So imagine you try to minimize a function p of y. So y is the variable, the decision variable. It's a vector in Rn, and p is a polynomial function. So we want to find its minimum over Rn. And let's say we have a single constraint, g of y in a negative, and again, g is some polynomial function. So I want to find the point y that satisfies g of y in a negative and makes the function p as small as possible. Okay, so my decision variable is a vector in Rn. How can you do this? So this problem is, and even if you forget the constraints, minimizing a polynomial of degree, let's say 4, is an NP-hard problem. So there is no way to expect to find a solution that works well all the time. So there are some compromises to be made. So I'm gonna show you a method to attack this NP-hard problem in a tractable way. And it's one of those things where it seems like we're gonna make the problem harder than it should be, right? It's like one of those crazy ideas where you really, if you just look at it at first, it really seems like we're making the problem harder. But trust me, these extra layer of complexity is gonna be worth it. And it's gonna enable us to attack this problem in a good way. So what is this idea? And if there is something you should remember from this slide, it's really this one. So instead of looking for vector y, what we're going to look for is a distribution mu over vectors y. Okay, so I'm not looking for a single point anymore. I'm looking for a distribution over points. So how is that helpful? Or at the very least, how can we reformulate the problem in terms of this distribution? So for example, I want to minimize p of y, right? What does that mean in terms of this distribution? Well, I'm going to say I'm going to replace that with the fact that I'm going to minimize the expectation or the average of this function p according to this distribution mu. Now, how about the constraint g of y in a negative? So I'm going to replace that with this complicated looking constraint. So let's parse it together. What is this saying? So this is saying that I'm going to be looking at expectations. So I'm going to looking at an average again of g of y. So the function that was present in my constraint, and I'm going to multiply it by the square of a new polynomial function f. So you really should think of f as a test function. So I take a test function, I square it, so I get something a negative. I multiply it with my function g of y, and I look at the average, and I ask from this big quantity to be in a negative. So right, so I take a test function, I hit my function g of y, I look at the average, and I want that to be in a negative. So I'm going to be replacing this non-negativity constraint with the fact that this average is non-negative for all test functions. Great. So so far we've only made the problem harder, but here is where things start to make sense. So when you think about this average, this expectation, taking expectation of a polynomial p, it turns out, and this is not very hard to see, that expectation is a linear function of my distribution mu. So whenever I take expectation, what I'm really taking is just a linear function of mu, and we love linear function in optimization because we can do a lot with them. And how to see this? Well, a polynomial, as we've seen before, is a sum of monomials times some coefficients. So when you take expectation, and expectation is linear, it's going to be the sum of those coefficients times the expectation of monomials, right? So if you're able to take expectation of these monomials, you can take expectation of polynomials. You know, if you can take expectations of the building blocks, you can take expectation of the full house, right? That's a different way of saying it. So, actually, you don't need to know the full distribution. You just need to know these sequence of moments, right? So I just need to know how to integrate or how to take expectation of monomials. And once you know the sequence of monomials, then, for example, if I ask you to express the expectation of P of Y, this is simply the sum of the coefficients of P times these moments mu alpha, right? And that's a really nice thing. So what we're going to do now is, remember how I said this test function could be any polynomial? Well, I'm going to limit that to be a test function of degree at most r, where r is an integer of my choosing. Think, r equals 2 or r equals 4 or something. So why do I do that? So again, if you think about this problem and how we've been kind of playing with it, instead of looking for a vector y, we're looking for distributions. So all of a sudden, we move to an infinite dimensional space, and not a particularly nice one. We're talking about the space of all distributions, right? And now in this space, everything becomes linear. So that's nice. So we paid the price of increase in the dimension, a blow up in the dimension. The dimension is really infinity. But the thing we gained is that everything is becoming linear. Now, of course, we cannot work with infinite dimensional spaces, when you do optimization, at least not directly. So what we've done, the first thing is to say, we only need moments. So at least this is a countable in many numbers. And by taking this test function to be up to degree r, what I'm really saying is I'm only going to be looking at moments, these sequence of moments up to a certain point. I'm going to truncate. So that's really the idea. So you live to the space of distributions, and then you look at the sequence of moments, and then you just look at the first moments. And this is I understand this is a mathematically heavy slide, and this is the hardest slide to digest. But what do I want you to take? What is the takeaway from this, really? There are a lot of details, but what do I want you to take away from this? I want you to take away from this the following. So before I do this, so we found a way, right, to express the problem in terms of distributions, right? And we've taken this test function to be up to degree r, right? So by requiring more from this test function f, I'm actually relaxing the problem. So that's how you find lower bounds. So the same reason that allowed us to make the problem finite dimensional also allowed us to find lower bounds for our optimization problem. And the thing is, of course, as r goes to infinity, as you relax the constraint that you have on these test functions, then you recover the true under some conditions, you recover the true optimum, right? But once you keep r fixed, r equals 2, r equals 4, etc., these problems, this optimization over these sequences of moments, finite sequences of moments, can be done by a semi-definite program. And this is really the nice thing here. So we've done a lot of work. We found another optimization problem that gives us lower bound on the original optimization problem. And this optimization problem can be solved as a semi-definite program, which we know how to solve. And if you've never heard the word semi-definite programming, in a nutshell, so this is the problem where you want to minimize a linear function. So C is a matrix, X is a matrix, X is our decision variable. And we want X to be a positive semi-definite matrix. So I'm really optimizing over the set of positive semi-definite matrices. And I have some maybe linear constraints on this matrix X. So semi-definite programming, one way to say it in one sentence, you want to optimize a linear function over the intersection of the cone of positive semi-definite matrices and the hyperplane given by some linear constraints. And if you've never seen semi-definite programming before, this is a particular, this is a special case of convex programming that we have good solvers for. So that's the thing to remember. All right, so that's the end of the detour. And now back to the moment optimization problem. So in this detour, hopefully the thing that should stick it into your mind is when you have a problem that is described by polynomial functions, you can attack it with these moment optimization techniques. You find a new optimization problem that gives you a lower bound, and that optimization problem can be solved by a semi-definite programming. Okay, so how is this? And again, if something is not clear, feel free to write in the chat or stop me and ask questions. So that's the end of the math, the new mathematical concepts that we're going to need for this talk. And now we're going to see how we can apply them to the motion planning problem. So in motion planning problem, there is an extra layer of complication, which is the fact that I'm not looking for a vector y, I'm looking for a path. So I'm looking for a path, so I need to parameterize it in some way that will make it, in such a way that makes the problem tractable. So the way we chose to parameterize the problem is as piecewise-linear path with a fixed number of pieces. There are multiple ways you could parameterize a path. You can say my path is a polynomial function. My path is piecewise polynomial function. My path is, spline given by splines, Bezier curves, etc. And the methods I'm going to show you will apply however you want to parameterize the problem. But arguably the easiest way to explain this, and also the method that we found is the most performance in practice, is this. So, this is the simplest possible thing. You say my path is small pieces and every piece is a segment, right? And, with piecewise linear functions, you can approximate pretty much any function you want. So there is no loss by, restricting ourselves to this family of paths. And, even if you have a small number of pieces, this could be a nice thing actually, because it can act as a regularizer. So when you have, for example, let's say 10 pieces, your path cannot do anything too crazy. 10 pieces is only so much. So that's like a nice side effect. So more precisely, you have your interval of time 0 to capital T, and then you split it or you divide it into S pieces of equal length. On, when you are in piece number I, you start from some vector ui, and then you move with constant velocity vi, right? So at time, in the piece number I am at ui, I look at the vector vi and I move along the direction vi with constant velocity until I reach ui plus 1, and then I follow vi plus 1, etc. You get the idea. So now the collision avoidance constraint is as follows. If my obstacle is given by some function g, I look at this function g at time t. And at time t, where am I? I am at point ui plus t times vi, as I just said. And I want this to be in a negative for all time t in this time segment. So if it was not for this, for all t thing, this would be simply a polynomial constraint, and we would attack it in exactly the same way I showed you, with moment optimization leading up to semi-definite programming, and then you solve it and then you get your results. But we have the for all time. So let's forget the for all time for now, right? So what would we have done if it was not for this quantification over time? So again, we would lift the space to the space of distributions. So I'm going to be looking at distributions over these ui's and vi's. And a nice way to look at this is you say, I'm going to be looking at distributions over paths, right? So this mu, you can sample from its feasible path to your problem. And we replace this constraint, this non-negativity constraint, with the fact that, if you look at the average of this quantity g that we want to be non-negative times some test function f squared, right? So exactly the same way that we had before, I want this to be non-negative. So we're going to replace the original negativity constraint with the constraint that says that some expectation should be non-negative, right? And this function f is, a polynomial function in these ui's and vi's. So it's an arbitrary function, arbitrary polynomial function of degree at most r. Okay, great. So again, if it was not for for all times, we would be done here, because this would be the same thing that I showed you during the detour, but I have for all time. So what is the best way to impose some constraint for all f, for all test functions, but also for all times? What's the best way to do it? So I claim that even though we have quantification over time, this is still in the realm of semi-definite program. So even when you have a semi-definite program that depends on time, that, where the constraint should be satisfied for all times, you can turn it to a vanilla semi-definite program where you don't have any dependence on time. And this is really an amazing result, if you've never seen it before, and if you work in a field where you worry too much about time dependence, in robotics, you worry about what happens over time. In dynamics, things change over time. If you can formulate the static problem as a semi-definite program, the time variant problem most likely will also be a semi-definite program, which is almost for free. So let me just spend a slide on this, because this could be of interest independently of the problem that I'm looking at today. So in a semi-definite program, you want to look at some matrix X, and you want it to be positive semi-definite, meaning all the eigenvalues are negative, right? But now imagine these entries depend on time, and I want this matrix that varies with time to be positive semi-definite for all times. So how can you impose this in practice? So if you've never come to this talk and you just encountered this problem in your research or your work, you would be tempted to just discretize time and say, I'm going to sample time points, and I'm just going to impose that my matrix is positive semi-definite over those sample points. And with enough sample points, if you impose on a grid that is fine enough, then the hope is between 2 time points, the matrix does not go, and no eigenvalue will go negative. And that's a fine approach that could work. The only problem with that is you're never sure that in between 2 sample points, you don't do something crazy, think something like Gibbs phenomenon or something that oscillates widely between 2 points. But also in safety critical applications, sometimes you want to be sure, you want to have a mathematical proof that the solution you found is a good one. Meaning I really want to make sure that my matrix stays positive semi-definite over the continuous interval 0 time. I cannot afford to have something that goes negative and my system would blow up or something. So this is where this result of that and student comes real handy. So it says that a time varying matrix is positive semi-definite for all times if and only if you can decompose X as follows. If you've ever worked with the sum of squares decompositions, this would look a little bit familiar. So this is saying, so let's parse it together. X can be decomposed as the sum of 3 terms. So each one of these terms is of the form some matrix transpose times the matrix itself. So whenever you multiply a matrix by its transpose, you get a positive semi-definite matrix by construction. And there are some weights here, T, capital T minus T, T times capital T minus T. All these weights are non-negative on the interval 0 capital T. So it's a little bit obvious that if you can decompose your matrix X as follows in this way, it becomes obvious, it's a mathematical proof that the matrix is positive semi-definite, that X is positive semi-definite over the interval 0 capital T. What is less obvious, and what this theorem is for, is that there is always such a decomposition whenever the time varying matrix is positive semi-definite, right? So it's an if and only if. And the good thing about this is that you can impose that decomposition by semi-definite programming. So I get a question here in the chat that this result requires some assumption on the matrix X of T. So thank you for that question, Jason. The only assumption about X of T is that it is a polynomial. So the entries of this matrix E, X, are polynomial functions of time. And that's really it. There is no other regularity assumption or anything like that. It's one of those nice results that doesn't have any hard to check conditions or anything like that. And one thing that I didn't mention and is really important is that this theorem comes with extra guarantees on the degrees of these matrices A, B, and C. The degree cannot be too high. So there is a bound in the degree, which means that the size of the semi-definite program that you will write eventually will not be too big. So again, a little bit of math, but if you've never seen this, so the only thing to remember is that if you have a semi-definite program and some constraint depends on time and you want it to be satisfied for all times, using this theorem from algebraic geometry, for which you don't really need to know the proof of this or how it works, you just need to know that it exists. You can turn that time varying semi-definite program to a semi-definite program that does not depend on time. And that's really the point. All right, so with everything that I've said so far, where are we? How did this picture change? So in order to find the shortest feasible path, you do this method that I just described. Use moment optimization, you take the test function, you bound the degree by R, and you get lower bounds. You get a lower bound on the length of the shortest feasible path. And these lower bounds get better and better as you increase this parameter R, this degree R of the test function. And we prove that as R goes to infinity, these bounds are tight, meaning these bounds, as R goes to infinity, converge to the length of the shortest feasible path. And the really nice about this is that each one of these bounds, you can compute with a semi-definite program whose size grows linearly with the dimension. And it's really a crucial property here and a little bit unexpected, because if you, for example, work with the sampling-based techniques like RRT, or a sample point, you would expect that the running time will scale, exponentially with the dimension. Each time you add a new dimension, you multiply the number of things you have to do by the dimension. So things scale exponentially, while here, these semi-definite programs as I've continuous time and so this gives you lower bounds, which is really, in practice, sometimes you want feasible path, you want upper bounds. You actually care about finding a path that you can feed to your controller, to your robot, or something like that. So we actually adapt methods that gives you lower bounds to a method that gives you upper bounds, that gives you feasible paths. Before I tell you the main idea, that it is the same as this voice, meaning you don't require time discretization, and it's based on semi-definite programs whose size grows.
Bashir, I think at least on my side, Bashir, at least on my side, you're breaking up a little bit over the last two slides. Maybe you want to switch off the video for the final part of the talk to be on the safe side.
Yes. You know what I'm going to do? I'm going to switch my audio to my phone. Yeah, sorry about that.
No worries, no worries.
Switch off my video, and
I think if you just switch off the video and you keep the audio also on this call, I think it should work out.
Yeah. Okay, can you?
You're still breaking up. I think you're connecting through the phone, so I just admitted you. Let's see if that works out.
Or okay, let me connect with my phone. Okay, can you?
There is a little bit. Yeah, I think that works out.
Okay, great. Yeah, hopefully you can hear me okay now. Yeah, again, if there is a problem, please let me know. And I apologize, but the bad quality of the internet connection here. Yeah, so I was saying, okay, if you just came to this talk now, and either you just came now or you didn't hear anything of the things that I've said before. So we're trying to compute the shortest feasible path to a motion planning problem. And I just presented a way that is based on moment optimization and semi-definite programming that gives you lower bounds. So lower bounds for 1, row 2, etc. So they're indexed by an integer, And you can control this integer, and the higher the integer is, the better bound you can get. But the bigger the semi-definite program you have to solve is. And we show that as this integer goes to infinity, these bounds actually converge to the shortest feasible path, to the length of the shortest feasible path. So these bounds are tight. And one of the nice things about these semi-definite programs or SDPs that you have to solve is that their size grows linearly with the dimension, which is unexpected because if you look at other methods, like methods based on sampling-based techniques like RRT, you would expect the size of the problem to grow exponentially with the dimension. Each time you add the dimension, you multiply the number of points in your problem by a constant. So each time it grows exponentially. And there is no time discretization. We handle continuous time constraints in a native way that does not require time discretization, thanks to this theorem that I just presented to you. Okay, so in practice, usually you don't care that much about, you care about lower bounds, but one thing you want more is to actually find upper bounds. You want to find actual path that you can feed to your robot or something. So we adapt this method that gives you lower bounds to give you also upper bounds, and we call it MMP, or Moment Motion Planner. And it enjoys some of the same nice properties that the method that gives lower bounds has. In particular, we don't require time discretization. The size of the semi-definite programs grow linearly with the dimension. So let me give you the main idea behind MMP. So how does it work? So again, we're left into the space of moments, of distributions, right? And at the end of the day, what we want is an actual path. So imagine for a moment, by some miracle, something happens and you find a solution mu that satisfies the following properties. So what are these properties? These are saying that the expectation of each variable squared is equal to the expectation of this variable, everything squared. So what is this saying? This is saying that the variance, basically the variance of this distribution is 0. Meaning that if you just look at the expectation of ui and vi, or said differently, this distribution is concentrated around a single path. And you can easily get that path by simply, for example, looking at the expectation, and that will give you the path. And this is really nice. So whenever this miraculous property happens, whenever you find that the variance is 0 of some distribution, it means it's concentrated around a single solution. And you can just take that solution to be your optimal solution, right? But in nature, there is no reason to expect that that's the case. There is no reason to expect that the solution you find by solving a semi-definite program will have variance 0. And as a mathematician, sometimes when nature does not go our way, we try to push it, to nudge it in the right direction so it does the things that we want it to do. So how can we do that? And here is a naive idea, and it will be our first out of 2 attempts. So the idea is to say, okay, I want to drive some quantity to 0. So let's call that quantity lambda, and let's add that lambda to our objective function. And since we're minimizing, hopefully, as we minimize, this quantity will go to 0, and then we will have variance equals 0. Can you still hear? Okay.
I can hear you, but I think you disabled the screen share, maybe.
Yeah.
Okay, now it's back.
Happens. Now you can see. All right. So I was saying, you add this new term, this penalty term, to your objective function. You minimize, and hopefully this term goes to 0. So the problem with this is that this lambda now is not a linear function. Actually, it's not even a convex function in mu, in our decision variable mu. And this is a problem because at the end of the day, we want to solve a semi-definite program, and I told you the objective function of a semi-definite program should be a linear function. So what can we do about that? And here is the idea that we came up with here, and this idea could be applied to in other situations as well. So how does this work? you say, okay, let me start with some random solution. Let's call it mu1. And by random, I just mean you just, either you start with the all zero function or you sample it according to some Gaussian distribution or something. And then you linearize the function lambda around this point mu1. So obviously, when you linearize a function, you get a linear function, obviously. And then you just solve your problem with this linearization of lambda. So you get a new solution mu2, and then you iterate. You linearize around the new, again, around this point mu2, and then you find the solution mu3, and then you keep iterating until some convergence criteria is met. And it turns out that this works really well. So that's really the full method. So you add a term to your, so again, to summarize here, you add a term that if it was 0, you would find the optimal solution. So you add that to your objective function, and then you minimize. Of course, that term is not convex, is not linear. So you linearize around some given point, and then you find a new solution, and then you linearize again around this new point, and then you keep iterating, and that's it until at some point, and then some convergence criteria is met, and you call that the final solution. And we found in our experiments that this method works extremely well. So it works fast because you can take this R that I was talking about earlier, this parameter that traces efficiency for precision to be 2, which is really the smallest thing you can take it. And then you can just iterate like 10 times or 20 times, and in under a second, you can find good solutions. So if you're bored of all the mathematical details, let me show you what everyone really wants to see, which are some numerical examples. We want to see this method in action. So let's look at this first example. So here I'm starting from this red dot, and I want to reach this other red dot on top. And the obstacle is this purple disk or ellipse. And where I am is in the green point. So you're going to see this. So you're going to see this green point try to get to the red point while avoiding the obstacle. So here we try to find the path of 10 segments. And this is really our method in action. So we use MMP with 10 segments, and we find this path. And then we solve the corresponding problem that gives you a lower bound, and which tells you that this solution that you found is actually optimal. This is the best thing you can do in this scenario. And here is a very similar example. So again, you can see how the obstacle avoidance is done. Sometimes the path thinks it's better to actually spend some of those segments of the path just waiting for the obstacles to pass by, and then you can cross. Here's another example in 3 dimensions. So we want to start from x0. We want to reach x capital T, and there are some obstacles that were generated that their position is generated at random, uniformly at random from the box. Each obstacle is some ball and moves with constant but random velocity. And we want to find the shortest path that avoids the obstacles. So here I'm comparing our method MMP with RRT. So MMP is this moment-based method. RRT is based on sampling and then computing this graph and finding path inside this graph. So why am I comparing these two methods? Well, both methods are successful in finding a feasible path, but let's compare the quality of these two paths, just qualitatively. So you can see that RRT, which is based on sampling, finds a path that is unnecessarily doing some crazy things, while the yellow path that is found by MMP, since we imposed that the path only has 10 segments, it's more straightforward and does not have a lot of these loops and going around, etc. So it's better quality because it's more regularized by design. In the paper that we have like more thorough experiments that you can time to look at. But today I just want to show you things more at a more qualitative level. So this is really the last thing I want to show you. So this is a robotics example. So let's say you have two robotics arms with like 3 degrees of freedom. You want to get them from the initial configuration on the left to the goal configuration on the right. So you can see that these two arms need to collaborate, not to collide with each other. So let's see how these three methods do. So MMP is ours again. RRT is this graph-based, sampling-based method. And on the right, I just put a method that is based on local search. So just apply, try to solve this optimization problem with some black box solver. So let's see what's happening. So if you focus on the right thing, this method based on which I call nonlinear programming baseline, it's not working at all because these two arms just collide with each other. So this method was not able to find feasible solutions. Now let's compare MMP and RRT. So let me play this again and focus on RRT this time. So you can see that RRT does unnecessary recoil at the beginning, this blue arm. It does this unnecessary recoil, but it succeeds in finding a feasible path. And now if you look at MMP, it's much better behaved, and it's this regularization, included regularization or regularization by design that makes the path, much more well behaved. And with this example, I will end the talk here. So thank you very much for listening. I know it's been a challenge given the quality of the internet connection. I hope it was not too bad and you were able to get at least something out of it. And I will put these slides on my website in case you didn't, you missed something or something like that. And please, if you have any questions, I'll take them now. And I'll put my video back on just so we can make the experience a little bit better for the viewers.
Bashir, I think this was fantastic. I think actually the disruption in the video was very minimal, at least on my side. So it was a fantastic talk. Thank you so much. There will be some round of applause here. It's a bit tougher, I guess, online. But
thank you, I appreciate that. I missed that. But that's the thing we don't have in Zoom, right? The automatic
I loved
it.
Yeah, but I love the introduction, actually the review you gave on moment relaxation, and I think you have a couple of results which are super interesting. So I do have a bunch of questions, but I want to open it up. Maybe I will break the ice with an initial question, and then we can open it up for the others to ask. I have questions about the composition from Det and Staden, but let me ask that later. Maybe let me start with the more surprising thing, which is this result on the linearization of the lambda and the convergence of the empirical approach. So in my understanding, the lambda, as you said, is going to be 0 if you have a tight relaxation, if you have an optimal solution. Is that the idea? So you kind of push the solution towards some tightness of a kind?
Yeah, yes, exactly. So, right. So the theme is this: whenever you do moment optimization, what you hope for is to find a solution that is concentrated around a single point. Again, so more broadly, what you want is, when you do moment optimization, you find moments or pseudo moments, and you wanna what people call rounding. You want to extract an actual solution from these moments. So you want to sample from these moments, which is not always easy or not always possible. And there are multiple ways to do it. But the easiest situation you can think of is when you compute these moments and you find that the distribution is concentrated around a single point, in which case you just look at the first order moments, the expectation, and you just take that to be the solution. It's not the only way, but it's definitely the most straightforward way to get a solution out of moments.
And in a sense, by enforcing these as in the objective function, by enforcing this condition to be true, I mean, are you biasing somehow the solution towards some local minimum, or are you biased
right.
the output of this? In a sense, it's surprising that you initialize at random, you linearize this, so you have very local knowledge from the linearization, and you still empirically get these very good solutions. Do you have an insight
right.
about what is the case?
Right. So yeah, so I will. So this method is not. These methods based on linearization and iteration is not guaranteed
right.
to find the best possible solution. And actually, these methods, the problem at heart is NP hard. So there is no reasonable way to find the best solution anyway. This method of linearizing, it has some guarantees under some very strict assumptions, and the same idea has been applied to other problems where moment optimization has been applied with different kind of guarantees. For this particular problem, there is no guarantee that it will actually converge or give you the best solution. But this is just a way that to just nudge the procedure in the right direction, so to speak. And in practice, it seems to work well. But at this time, we don't have like guarantees that give you that, that guarantee that this will give you the best possible solution. But this was an adaptation of the other methods that gives you lower bounds that I presented earlier. And for this one, we actually have guarantees that it converges as the size of the problem grows. But we found that this, when the size of the problem grows, when R increases, the size of these SCPs actually get a little bit out of hand. So we adapted it. We try to push the solution in the right direction. Maybe we do some local bias, like you said, maybe you do, but in practice, it seems to work better. And it's one of those things where, in theory, we should do one thing, but in practice, some other method that seems to do better. And again, this is really a good, good problem for which we don't know how to prove much. So if there are some students that are really interested in this and looking at this with fresh eyes, maybe they can find some nice guarantees, and that would be great, because it's one of these things that works well in practice. We don't understand very well in theory why that's the case. We just have a vague intuition, and if someone comes in and can say something more about this, that would be fantastic, actually.
I think that's on the robotics side is still very, very interesting, right? If you have an approach that works well, is fast and so on, but maybe let me push a little bit more. And let me ask you, I understand that for the lower bound, these will get to the optimal solution for R increasing, right? But for the empirical approach that you are saying in the last part of the presentation, so what you observe is that the approach empirical is better than the others. That's for sure is true. But do you observe also empirical optimality in the sense that, if you run this approach, which is fast, and then you check against lower bounds, do you see that most of the cases gets the optimal solution?
Right. So, okay, I should be careful. So I'm not saying that this method that we propose is doing necessarily better than the other methods. It really depends. I mean, in these examples that I showed you in dimension 2, dimension 3, it seems to do better. The nice thing about this method is we can detect optimality. So you can solve the lower bound, and if the lower bound matches the upper bound, like for example, I think almost these examples that I showed you, for example, these two-dimensional examples, what I'm showing you is what this heuristic finds. We also solve, of course, the corresponding lower bound problem, and it gives us a number, and if it matches, then we know we're optimal. So that's really a nice thing. But sometimes maybe you don't find the best solution that could very well happen. But like the thing that I like about this method, it's like based on an actual method that is guaranteed to work with a small modification. So there is more hope to be able to prove something, some stuff about it, like bounds and things like this. In practice, might not be the best method out there, but it's different from the rest. So it can work in areas where other methods do not work, and also there is hope to prove something more about it. And that's really the thing that makes it interesting to me.
Thank you so much for the answer. So I want to give the chance to the others as well to ask. For the attendees, you can either ask in the chat, or you can simply unmute yourself and ask. And let's see if there are more questions.
Hey, Bachir, great talk. One quick question, and you probably said this earlier, maybe I just missed it. One thing you emphasize is the STP size grows linearly in the dimension. Why is that? Is it not? Why is it not like some thing you'd expect that's a combinatorial growth in the degree R and the number of variables n?
Right. So the reason is really this, right? Let me. What's the best way to say this? So when you do moment optimization, right, and you write the semidefinite program, so you have you start with a polynomial optimization problem, and now let's say you look at order 2. Let's say you do the moment optimization at order 2. If you just increase the degree of the polynomials, the size of these STPs, will grow linearly. If you're looking at order 2, R equals 2, right? In general, the size of the semi-definite programming relaxation will grow polynomially in the degree of the polynomial. If you keep, so again, let me just say that again, and let's forget the because this is really an interesting point. Let's forget the motion planning problem, right? If you do moment relaxation and you write the SDP relaxations, right? How does their size depend on the degree and the number of variables? If you fix either the degree or the number of variables and you let the other one vary, then the size of this SDP will grow polynomially. And actually, if you look at the second order relaxation, the size will grow linearly, which is really nice. To your question, when you increase the dimension, what this means is you increase the dimension of these UIs. So you're basically increasing the degree, and you're keeping the number of variables. The degree is fixed, and you're changing the number of variables, right? So that's what's happening. So if you keep everything fixed and you just change the degree, the size grows polynomially, and in this particular case, it grows linearly because of the way we chose R.
Isn't it quadratic? If it's 2, isn't it m plus 2?
Okay, linearly, I mean, yeah, linearly, I mean each dimension of this matrix grows linearly. Of course, the size of the full matrix will grow quadratically. You're right about that. And the time to solve the SDP will not grow linearly because the solve time also is not linear in the size of the matrix. It's some polynomial. But the thing is, it's not exponential. That's really the point. Does this answer the question? Maybe I answered some other questions that happen sometimes.
I think I understood most of it. I certainly agree that if R is fixed, then the number of variables grows polynomially with a degree that's roughly R. But I think I didn't quite catch the thing you said at the end about the second order relaxation, where you go from polynomial to linear. I think that's also Hung's question.
Oh, okay. Let me say it again. So let's say R is fixed. So we're looking at the second order. Let's say R equals 2, the smallest possible thing. R equals 2. You're looking at the second order moment relaxation. Let's say so your constraints, the degree is fixed. For example, let's say all the constraints are quadratic, right? Everything is given by, you just increase the dimension, right? So increasing the dimension, meaning these UIs and VIs, their size increases. So now if the degree is fixed, if the order of the relaxation is fixed, you just change the number of variables, the size of the STPs is gonna grow polynomially in the number of variables. And on top of this, if the order is 2 and the degree is quadratic, these things actually grow linearly, meaning the matrix, each dimension grows linearly, which means the matrix as a whole grows quadratically. Again, the intricacies, we have more details in the paper, but the main idea here is that if the size of these STP relaxations, if you fix the degree and vary the number of variables, or you fix the number of variables and you vary the degree, the size grows polynomial. That's really.
I think by R equal to 2, do you mean the first order or second order?
I think first order. Yeah, I call it.
Yeah, you mean first order, right? Yeah, I think because
I call it second because R equals 2. You're right.
Yeah, but the order can only be odd, so that's why 2 it's lowest order, right? So that's why it's linear. I think now I get it.
Yeah. Okay. Sorry about that. Yeah. Okay. So I call it. Okay. Yes. Sorry about that. So
okay,
when
only be even.
R equals 2 corresponds to the first order Lasserre hierarchy. Yes. Yes. Absolutely.
All makes sense. Thanks so much.
So Bachir, I have another question, which is I didn't quite get it. So the last thing that you do with linearization and then solving SCP again and again in an iterative way. So does this solve the problem of satisfying the constraint? Because for general POP, finding a feasible point is kind of difficult, right? Typically, like you said, that if you solve the relaxation, you just take the order 1 moments and then you do some type of rounding, but right. Then the rounded solution may not be a feasible point. Right? Does this approach solve that feasibility issue?
So if at some point of this iteration, you find a solution that satisfies these 2 constraints, which we were nudging the solutions towards, then yes.
Why why these conditions guarantee that the solution is feasible?
It's so well. The SDP already has constraints coming from. So the SDP that we write already has these as constraints. So when those two conditions that I just highlighted are true, it means that these pseudo moments are actually moments of a true distribution, right? Or said differently, then this expectation is actually just equals to what's inside the expectation, because there is only a single point this measure is concentrated on. So this is true actually for any time you do this Lasserre type relaxations. Whenever you find out that the moments you have, like are tight, meaning that you find something like variance equals 0, it means that what you found is actually an actual distribution, and on top of that, that actual distribution is concentrated around a single point, and that single point obviously will satisfy all the constraints because the expectation is just it's just equal to what's inside the expectation evaluated at that single point. If that makes sense. Like the hope always with Lasserre hierarchies is to find pseudo moments that are actually actual moments. So whenever you do that, it means that this distribution is supported on the true feasible state of the original problem. And if on top of that, the distribution is concentrated around the single point, then that single point obviously satisfies the.
Does that lead to a rank 1 moment matrix?
That's exactly what it is. So
okay,
these two conditions, you can view them as just determinant equals 0 of the 2x2 first minor, right?
Oh, okay.
Or like where Cauchy-Schwarz is tight, or different ways to look at it, right? You just look at the variance matrix, and the variance matrix has rank 1. That's at most 1. That's what this is saying.
Is there just following up on that question? Like, is there any? So there are other ways to enforce or to encourage rank 1 solution. Thinking about nuclear norm minimization, things like that. Would it be a valid replacement there?
Yeah. So that would be also a different way of doing this. So we just picked this way to do it. You can add different types of regularization. That's a very good point. You can minimize the nuclear norm of this. Again, with Lasserre hierarchy, you have this matrix of moments, of pseudo moments. You want it to be a matrix of moments. And one way to do it is to have its rank, you want to have some rank condition. And rank 1 is the most straightforward, which means you have a single point your distribution is concentrated on. And any way of any proxy for rank, nuclear normalization, even L1, this kind of things, or these iterative kind of minimization. Or sometimes people minimize log det or something like that. So yeah, any one of the proxies for rank will be valid. So yeah, again, our hope is to take any valid method that people usually use for rank 1 and adapt it to this time dependence. There's a little bit of issue with time dependence, but yeah, that's the idea.
Fantastic.
But in our test, we found this to be the best. We compared different methods, and this seemed to be the fastest and the one that gave the most promising results.
Great. Okay. So I think we have a few more questions, Bachir, but I want to make sure that that's okay for you. We're running out of time. Do you have a few more minutes for questions?
Oh yeah. Oh, we can go all night if you want. Well, I say night because it's 8 p.m. for me, but yeah.
Thanks again for your time.
I'm happy to stay. Yeah.
Okay, I will move on and ask a question from the chat. Jingran is asking 2 questions. First of all, in the experiments, are the function g and the paths of the obstacles known beforehand? And the second question is if you can provide more details about the runtime for the experiments. Right. Runtime, more than the complex, runtime in seconds or things like that.
Yes. So let me. So G is known. G is perfectly known. We did not handle a problem where G is not. We can talk about how to adapt our methods to that set time, but G is completely known. The R that I talked about is equal to 2, so that corresponds to the first order of Lasserre hierarchy. R equals 2. The number of pieces in our path is 10 in all the experiments. Okay, what more can I say? In this experiment, all the obstacles are given by quadratic functions G. So in terms of runtime on a normal machine without any special optimization, all these paths can be found in under a second. so that, like where and the number of iterations. So I talked about this iterative thing. I took 20 iterations, but that's really way too much. I mean, you can get away with 5 or 6 usually. I took 20, so I'm solving like 20 smallish semi-definite programs and in under a second. So that's basically what's going on here. For the others, it was similar runtime. I don't remember exactly, but I think it was either like a little bit more or a little bit less than a second for all of these. Again, these are quadratic constraints in dimension 3. For this last example, so you cannot really see what the constraints are. So the constraints are, you can think about this space as 3-dimensional, and each configure. So there are like 3 degrees of freedom for each particular value for these degrees of freedom. If that particular value makes the arms collide either with each other or with themselves, then that point is considered an obstacle. And we approximated those points by ellipsoids, so again, quadratics. And I think we had like 10, like we covered those points with 10 ellipsoids. Anyway, so again, it's like quadratics. We have like tens of constraints and the degree of the size, yeah. And it runs under a second.
Great, and I think there is a question from Jean Bernard.
Jean Bernard, yeah, I can see the hand is.
Yeah, thank you. Hello everybody. Maybe you could say, Bachir, that experimentally the dimension 3 is easier than dimension 2 actually. And
oh yeah, so right.
Yeah, because there is more space.
Oh yeah. I completely forget about this. So actually, what we found in our experiments is that dimension 2 was the most challenging. And the reason for that is, in dimension 2, you don't have a lot of degrees of freedom. So, in order to find the feasible path, it's very hard. And especially since we're, you mentioned this local optimization thing, like where I'm initializing things at random. So things are very sensitive to the way you initialize them in the first place. In higher dimensions, there is a lot more free space around, right? So even if you initialize things at random, you will find things that almost work from the first run. And this iterative way of looking at things actually improves. Like if things are very close to optimal to start with, they will improve them very fast. So in our experiments, which is actually a funny thing, the higher the dimension, the easier the problem gets. And yeah. And actually, for this experiment, which has 3 degrees of freedom, we experimented actually with 4 and 5, and we found that it got too easy at those points to find feasible paths, and it's easy to like optimize, like it's the the curse of dimensionality, but the other way around. Sometimes in higher dimension, things sometimes gets easier, and since we don't pay a very high price for higher dimension, we gain a lot by having this extra space. If the runtime, was scaling exponentially or something, then that would not necessarily be worth it. But it seems that with this particular method, it seems to work well with in higher dimension.
Very interesting. It's very counterintuitive, but it's quite interesting. Okay. I do have a couple of extra questions, maybe, but let me make sure that the others have the chance to ask.
Hi, Bachir, I have a quick question. I'm just curious, if you go to a higher dimension, but you keep the same order, do you see that the optimality gap between your upper and lower bounds grows? Because I guess intuitively, I would expect that, at least in some cases, you may kind of need higher order and higher dimensions to, fit in the tight corners or something. Do you see that happen? Based on your last response, it seems like maybe not, but.
Yeah, no, for this, at least for the experiments we've done, it seems like the opposite is true. It's easier to get to the optimal solution in higher dimensions because it's just the way this method works. So I mentioned it's iterative, so it keeps improving little by little the solution that you get. It's like it satisfies the constraints more and more. And in higher dimension, there are so many dimensions where you can perturb the solution to make it satisfy the constraints. It just seemed that in higher dimension, actually, this gap of optimality gets lower. Yeah. But of course, they will depend on the actual applications. Depends on the type of obstacles that you have and things. But right. At least if you're in a box and the obstacles are given by balls and then they're moving around, the higher the dimension, the easier it gets.
Yeah, back to the intuition is that suppose you have m obstacles of cubes of size a, so the volume is a cube. So if you put all those m obstacles in dimension 3 in a cube, the portion of volume they occupy is smaller than dimension 2. The same m obstacles with square in dimension 2, so it would be a squared surface for each obstacle. And if you have m of them, so in dimension 2 they occupy more space in the cube 0, 1, for example, than the same m obstacle with volume a cube in the big in the 0, 1 cube space. That's the reason why in dimension 3 it would be easier than the portion of space occupied by the obstacles is less in proportion in dimension 3 than in dimension 2.
Mm-hmm. Okay. Yeah,
and to take it to the extreme, in dimension 1, if you have one constraint,
yeah,
it will actually cut out. There is no feasible path, right? That's another one.
Yeah, I think I was also thinking about if in higher dimensions the POP that you get, in terms of objective and constraints, do the polynomials get sparser in higher degrees? Is that the reason why it's easier to get tightness in higher degrees?
I wouldn't say they get sparser. I mean, for example, if you have like a ball, in higher dimension, the sparsity is this. I mean, it's true that the number of monomials doesn't scale exponentially with the dimension. It scales linearly with the dimension, but But this point that you mentioned,
it is kind of true. It becomes sparser, right? Because in dimension 2, it's like if you were to specify a circle, it's like x1 squared plus x2 squared equal to 1. If you count the terms, there are 2 terms, and but the number of total terms is m plus 2 plus choose 2, right? But if at degree 3, then it's x1 squared plus x2 squared plus x3 squared equal to 1. Then you have 3 terms, right, but the number of total terms is actually not linear. So the terms is linear, but the number of all possible terms is not linear. So that's why it is getting sparser in the sense.
The proportion of monomials that you actually use. It gets
sparser. I mean, or something like that.
That might be true, like for higher degrees. For degree 2, like if you take a quadratic that is like an ellipsoid or something like that, this is not aligned with the axis, you would use all the monomials, but I wouldn't expect the efficiency of the algorithm to change that much. But maybe when you move up in the dimension, you don't necessarily use all the monomials, and that could help definitely, especially for higher degrees, right? For quadratics, I don't see it, but for higher degrees, that could be the case. And but you touched on a good point that when we use these STP-based methods, there's a lot to be done. Like so far, we have not really used sparsity. I didn't talk about how to leverage sparsity. There are ways to actually make the size of these STPs much smaller by taking advantage of that explicitly. There are other methods to handle STPs rather than solving them exactly. There are ways of approximating them. There are methods like DSOS, SDSOS that solve linear programs and second-order cone programs that approximate the solution to the STP. So that's also another way to scale and get faster solutions. I mean, so it's very rich fields, and there are a lot of, one thing we don't know yet how to do perfectly is how to leverage the structure of the problem to make solving it a lot easier. There's a lot of work that handles sparsity very well, like taking the sparsity graph of which monomials are present or not, but there is no systematic way of taking advantage of everything at the same time. But so there is a lot of work to be done in that direction. And sometimes you get results for free. Sometimes you get, just because the problem is sparse or something, you get good results just by applying things as a black box. And that could be happening here. For higher degree, the number of monomials that you use may be smaller than the number of available monomials, etc. Yeah.
Very cool.
Maybe one last question is more of a curiosity. I don't know if that's a real problem, but I don't know. I imagine that if you start increasing the number of segments, right, at some point you're going to start having ambiguities in the solution, right? Maybe one segment can collapse to zero, like, another segment. So you start having multiple solutions in the optimization problem. While it seems that the heuristic with the lambda is kind of enforcing, or is encouraging, finding a unique solution somehow. Do you see, are there problems if you have some ambiguity in the solution?
Yeah. So one thing we noticed, if the problem is perfectly symmetric, right? So that's another way of saying there are two solutions. One goes upwards and one goes down, right? So it's the same idea. And the way we're doing things, we're trying to push the solutions toward one of them. So when you start with things at random, hopefully that biases the solutions toward one of them, and then it just pushes toward, it just forgets about the other solution. So that that's why initializing at random worked well for our case. But if you initialize from all zero, sometimes it didn't work, and we did not really understand at the beginning why. But it was exactly this reason, that there was perfect symmetry, and the solution just could not make up its mind which one to be concentrated on, because we really want this distribution to be supported on a single solution. So that thing happened, and as the number of segments increases, sometimes you get that. Sometimes if there are two ways to go around an obstacle, we observe this phenomenon where it takes a lot more iterations, for example, to decide on which side to go from. Yeah, definitely.
Makes a lot of sense.
I would say one thing that helps, initializing at random, but also increasing the R. So sometimes things that are symmetrical and ambiguous, when you just look at moments of order 2, when you increase the degree, you get more specific, and you get more monomials to actually differentiate the solutions. And sometimes that helps too. You go up in this R, and it helps the solution make up its mind easier. It's one of these things.
Understood. Okay, that's very cool. Okay.
Is
All
this?
right. Yes.
I'm looking at this slide. So, is this sort of numerically kind of similar? I don't know. Is this similar to solving a non-convex constraint STP? So basically, this looks like you are solving a linear STP subject to these non-convex constraints on some of the entries, right? And it looks like you are solving it using some sort of penalty method that you linearize, and then you solve something again. You linearize. Is this SQP symmetric, SQP type method for generic nonlinear programming? Looks similar, but probably not exactly the same.
It does. Some people applied similar techniques to, you mentioned, it's like having an STP with a non-convex constraint. And more specifically, the non-convex constraint here is that we want the rank to be equal to 1. Yeah. People have tried different proxies. Yeah, like a penalty term, exactly like you said. You minimize log det, or you minimize the trace of the matrix, or So this method of doing things applies more broadly than this problem. So whenever you have an STP and you want a solution of low rank, this could work. Or more generally, if you have quadratic, non-convex quadratic constraint that you want to impose, this could be something to try.
Yeah, thank you.